Force law for simple harmonic motion. We have concluded so far that acceleration is proportional to the displacement, or you might say this is minus omega square x. This is taken here as a vector, although there is no practice of putting the vector symbol, but we do consider acceleration here as a vector and displacement as a vector. Minus sign indicates that both are opposite to each other. If you write down the force regarding or associated with this acceleration, it's going to be m omega square x. This is force and this would be written as k. This is called force constant k m omega square. Restoring force F and displacement is x. Both are directly proportional. This is one of the important three characteristics of simple harmonic motion, that here the restoring force is always directly proportional to the displacement and opposite to the displacement also. That thing has been mentioned over here. K is known as force constant, as you notice in the case of a spring. When a spring is pulled or even compressed, then a force acts that tries to restore it, and that force is directly proportional to the displacement. That's known as restoring force, or you can say elastic force, and that is also given by this relation where you called K as a force constant. Here also K would be known as force constant. This law becomes condition for all types of SHM. Restoring force is only responsible for restoring the body or bringing the body back to the mean position. Now, if you want to plot the graph between force, restoring force and displacement, certainly it's going to be a straight line. But since it is with minus sign, you could choose the side that's in negative side. You are taking the displacement here along this axis. So, better you choose this side. This is the restoring force. This is displacement. Restoring force and displacement. Same would be the graph for acceleration and displacement. And you know the area of Fx graph is going to be the work done or the energy stored. If you try to find out the potential energy stored this way, this is going to be half Fx, then half F would be Kx into x, that is kx square, and already I told you k is m omega square, this is x square. So, one very important formula you derive here for the potential energy for the body oscillating, or you could say it is the potential energy of the oscillator in the form half m omega square x square. See, don't be confused with this relation half kx square, because k is representing here m omega square itself. The conditions for SHM have been given. First is it should be to and fro motion. Second is that acceleration should be opposite to displacement. Third is acceleration is directly proportional to the displacement. The values have been given here for force, acceleration, angular frequency, time period and frequency. And in coming lectures, when we cover the types of pendulum, in that I'll tell you different pendulum have different values of constants. Most essential condition for simple harmonic motion is that displacement, velocity, acceleration, all are variable. They change with distance and with time as well. For the potential energy, we have derived one term that is proportional to x square. So, important feature that you get here is that potential energy is directly proportional to square of the displacement. That is, you could say, a parabolic relation. Now, we try to find the term for kinetic energy. Kinetic energy, you know, is half mv square, and you know here the velocity is given by omega root a square minus x square. If you square whole thing, you are going to find the term for kinetic energy, that is half m omega square a square minus x square. Just now we studied that potential energy would be given by half m omega square x square. You see, they seem to be complementary of each other, means here x square is with minus sign and here it is with plus sign. That means when x makes u maximum, obviously it will make k minimum. It is crystal clear that the two values can never be maximum or minimum together. If one is going to be maximum, the other will be minimum at the same very time. If you want to sum up the two, that is, you want to find the total energy, sum of kinetic and potential, these two terms x square plus and minus will get cancelled and you will get the final relation for total energy half m omega square a square. So, these are the three terms. Total energy is having one very important characteristic with itself, that it is not having any term with displacement. Regarding displacement, you could say this is independent of displacement. What does it mean ultimately? It simply means that it remains constant throughout. Total energy in simple harmonic motion is going to remain constant throughout, whereas the kinetic and potential will go on changing regularly. In the mean position, kinetic energy will be maximum. In the extreme position, potential energy will be maximum.